Okay, welcome back. Today we're going to be talking about the net force and Newton's first law. Now to calculate, when we talk about the net force, what that means is the sum of all the forces acting on a particular particle. And that's going to be the important thing for determining its motion. Because the net force tells us what the change in motion is. Remember though that force is a vector. And that means that when we add all the vectors, all the forces together, we're adding vectors. And adding vectors is slightly more complicated than adding scalars. So the first step is going to be to draw the free body diagram. Second step, pick a coordinate system, and you'll want to pick it in such a way that it makes adding the vectors easy. So then you calculate the x and y components of each force, and then add them together to get the components of the net force. And depending on the situation, you may need to find the magnitude of the net force as well. But in general, if the net force equals 0, then the acceleration is also equal to 0. That's Newton's first law. And if the x component of the net force equals 0, then the x component of the acceleration equals 0, and so also for the y component and z component. So generally, if there's a component of if the net force in a particular direction is non-zero, then there will be an acceleration in that direction. So here's an example. We have three forces that act on a particle. First one has a magnitude of 130 newtons, points west. Second one has a magnitude of 90 newtons, points 40 degrees north of east. And third one has a magnitude of 80 newtons, points 10 degrees east of south. So what we need to do is first we draw a free body diagram. So the first one points west. It has a magnitude of 130 newtons. Second force points 40 degrees north of east. So there's F2, which is 90 newtons, and that's 40 degrees. And F3, 10 degrees east of south. There's south. There's 10 degrees east of it, and it has a magnitude of 80 newtons. Now what we'll do is we'll find the components of F1, F2, and F3. F1 has an x component of negative 130 newtons. We'll pick our x and y axes normally, and its y component is 0. F2, we'll have to do some trigonometry. So we've got its x and y components, and its x component is clearly adjacent to the 40-degree angle, so we'll use cosine. And we find that it has an x component of 68.9 newtons and a y component of 57.9 newtons. Now F3 will do something similar, but when we go to draw the triangle for F3, we notice x is now opposite the 10-degree angle, and so we'll use sine there. So 80 sine 10 degrees is 13.9 newtons. And its y component is adjacent, so 80 cosine 10. And we get 78.8 newtons, but notice that it points downwards, so we're going to make that negative. And so there's our components of the forces. Now we've got to add them up. So negative 130 plus 68.9 plus 13.9 gives us an x component of negative 47.2 newtons. And the y component, 57.9 minus 78.8, works out to be negative 20.9 newtons. So there's our x and y components of the net force, but we need to find the magnitude and direction. I'm just going to find the magnitude. You can get the direction later. So the magnitude, we just use the Pythagorean theorem. And we get a magnitude of 51.6 newtons. The direction is going to point somewhere into quadrant 3. I'll let you figure out the exact angle on your own for practice. Now, the next term we're going to learn is something called equilibrium. What that means is that an object is not accelerating. And we know that force causes acceleration, so if the object is not accelerating, that tells us F net equals 0. Oh, that's what I said later in the slide. Oh well. And there's two kinds of equilibrium. Static, where it's not moving, and dynamic, where it's moving, but the velocity is constant. There's no difference dynamically. Net force is going to be 0 in both cases. And Newton's first law, its most common formulation: object in motion tends to remain in motion, and an object at rest tends to remain at rest, unless acted upon by an outside force. Or another way of saying it, force causes changes in motion. So here's an example. A block, which weighs 40 newtons, is sitting on a ramp inclined at 25 degrees. Find the magnitudes of the normal and frictional forces. Now we know, because we drew a free body diagram before, that we have the weight of the block is 40 newtons. And we know that it has a normal force, and it has a friction force. And we're told that it's sitting on a ramp, which implies that it's not moving. And that means F net equals 0. And here we see why we want to use this coordinate system, where x points down the ramp and y is perpendicular to the ramp. Because now normal force and friction force line up with the coordinate system, and the weight force is now 25 degrees off of the y-axis. So we'll make our list of x and y components. We've got normal force, frictional force, and the weight force. So the normal force, notice that its x component is 0. And its y component we don't know, we'll just call it n. The friction force, its x component is negative f, where f is the magnitude of the friction force, because it points up the ramp. And I'm going to change colors. And its y component is 0. The weight force is the tricky one. And by tricky, I mean not that tricky. Anyway, we have a vector. We want to find the components of the vector, so we're going to draw a right triangle. The hypotenuse is the force, and then it's got its y and its x components. Notice that the x component is opposite the 25-degree angle, and so we'll say it's 40 newtons sine 25. Also notice that that makes sense, because the larger the angle gets, the more the weight force tends to pull it down the ramp, and sine increases as the angle increases. Similar calculation, but using cosine for y tells us that it's 36.3 newtons, but we've got to make that negative because we define positive y to be upwards out of the ramp. And this is 16.9 newtons. Now what we do is we sum all the forces. In the x direction, we have 16.9 newtons minus the friction force. And that has to equal 0 because the block's not moving, which tells us the friction force is equal to 16.9 newtons. And then in the y direction, we have normal force minus 36.3 newtons. That's also equal to 0 because it's not moving. And so we find that the normal force has to equal 36.3 newtons. Okay. Last slide. We've got a bird sitting on the power line, and you should have drawn a free body diagram before, so this should be easy for you. Essentially, you've got two tensions, which we're going to assume are equal, so we'll label both of them T. And those are 6 degrees, not 60, 6 degrees from the horizontal. And then there's also the weight of the bird, which is 4 newtons. We want to find the tension in the power line. Now we're going to use a coordinate system that looks like this. Only one force lines up with it, but also notice the symmetry here. If we make our table, we've got, I'll call this T1 and T2. Actually, we're not going to make a table. We're going to be physicists, and we're going to see what's going on physically rather than just going through the formalism. It's obvious that if these two tensions are equal, then we have symmetry over the y-axis. And so that means we can say that T1x equals negative T2x. So their x components are going to cancel out, and their y components, T1y, is going to equal the other y component. And the result of this, if we sum all the forces in the y direction, we get twice the y component of the tension minus the 4 Newton weight equals 0 because it's not moving. So that means the y component of the tension is equal to 2 newtons. But now we need to, we're looking for the tension, and so that means the magnitude of the tension. So we've got the y component of the force and the angle. So we'll draw our triangle. Hypotenuse is what we're looking for. We know that angle is 6 degrees, and we know that that is 2 newtons. And so we say that 2 newtons over t equals sine 6 degrees, and t equals 2 newtons divided by the sine of 6. And that comes out to be 19 newtons. What you should ask yourself is, how much would the tension need to be if the angle was 0? So if there was enough tension that the bird didn't cause the line to sag at all, what would the tension have to be? Also, for tomorrow, I will be checking questions 3 and 4.